So hi everyone, my name is Efrat Ravid. A quick check before we start today. How many of you have heard of Wordle? Okay, that's good. And how many of you play or played Wordle? Good crowd, very good crowd. So today we're going to introduce some techniques for programming agents that can automatically solve Wordle. Now, before we continue, let's close the gap for those of you that don't play, or maybe you forgot already. Wordle is a simple online word game. It was launched late October last year and exploded virally. After it trended so much, then the New York Times bought it from the original developer. The developer originally wrote it as a gift for his girlfriend because she likes word games. And the New York Times bought it from him in the low seven figures. So even made a small fortune by being a good boyfriend. So the goal of the game is to guess a 5-letter English word in up to 6 guesses. But every Wordle player will tell you that the real goal is to guess in as little guesses as possible. Now, every day there's a new word, and it's the same word for everyone worldwide. So you can share it on social media and compare with your friends. How many guesses did it take me today and things like that. So after you guess a word, each guess needs to be a valid English word. And after the guess, you receive back feedback regarding the word you guessed, which is a pattern of gray, yellow, and green tiles. Now, a gray tile means the letter you guessed isn't in the target word. A yellow tile means it's in the target word, but not in the spot where you guessed it. And a green tile means it's in the target word where you guessed it. Now, another important thing to say before we go to the next slide, the target word is a common English word. Okay, so it won't be something like obscure or something like that. So let's quickly go over what we're going to talk about today. So first, we're going to talk about non-machine learning based techniques for solving Wordle to later justify the use of machine learning. We're going to introduce the Wordle benchmark Python package, which is an environment for simulating Wordle games, a very easy one. We're going to dive into 2 techniques for teaching agents to play Wordle. The first uses reinforcement learning, and the second is based on principles from information theory. And finally, we'll compare between all of our agents and find out which one leads to the best strategy. So, like I said, my name is Efrat Ravid. I'm the lead data scientist at Integer, where I lead a team that develops models for cyber threat detection. You might be asking yourself, then why am I here standing and talking about machine learning for games? Well, it's because I'm also a Wordle player like a lot of you. And when I started playing, the data scientist in me kind of started itching, and I asked myself, how good can I play, and what's the best guess at each steps, and questions like that. So that's why I started looking into what techniques are out there for solving games in general, and specifically for Wordle, what's out there to play the game. So one of the first questions I wanted to answer was, do we even need machine learning to play Wordle? It's a pretty simple game. And we can probably write some logic based on what we do as human players that will do not that bad. So my first attempt was writing an agent that just randomly guesses a word each step. I mean, the number of 5-letter English words is finite, and it's even not that much. So you can just go over all the remaining possible words each step and randomly guess. But then I thought to myself that when a human plays the game, he does try to guess strategic words. For example, words with vowels or words with common letters. So I added a quick improvement that guesses each turn the word with the most frequent letters. And I learned letter frequencies based on the list of 5-letter words. Just counted appearances of the letters in the words, and then chose the word with the most frequent letters. So this might sound kind of hard to sit down and write your own agents, but to do so, I use the Wordle benchmark package. It's an environment for simulating Wordle games with a very easy interface. it takes off of you all the heavy lifting of like coding the game itself and things like that. So if you want to write your own agent, all you need to do is implement an agent. What you see here is that simulating the game is 2 lines of code. It's like actually 2 lines of code. So you receive back after the simulations the results, which contain the average score of your player in the game, which is the average number of guesses it took it to guess the target word. And that's also the metric that we're going to follow in our talk. So implementing an agent is also very easy. Here you see the agent that guesses the words better based on a letter frequency. So what you need to do is take the package's agent class, implement the play method that receives an instance of the game. The instance of the game can have has the history of the game, like how many guesses did it take you up till now, and what were your previous guesses and things like that. Here you can see I used the game to calculate the possible remaining words. And for our first results of the day, so an agent that guesses randomly achieved an average score of 4.9, and an agent that guesses based on letter frequencies achieves an average score of 4.48, which is actually not that bad. I mean, I was pretty surprised with the results. I still wanted to check like how good is it. I found online a project that collected tweets where people shared their Wordle scores, and based on that calculated like average human performance. And an average human achieves a score of around 3.92. So can
I just ask them? A person who's donating their score.
It's an optimistic score. Yeah. That's what. Okay, it's an optimistic score. Yes, we're gonna beat it anyway, just as a spoiler. Okay. So in general, though I was surprised how far simple coding approaches do get us, we still achieve results that are far from human performance. So this brings us back to my original question. Do we need machine learning? I mean, we can keep manually coding improvements in our agents. For example, we can add we can teach it to take into account letter positioning and not only letter frequencies. But this is pretty endless and will probably also limit us only to human performance. Now, instead, machine learning lets us train an agent that learns the general motion of what a good guess is without us needing to tell it explicitly. And hopefully, by that, we'll get an agent that's better than human play. So let's talk about our first technique for today. The first technique is reinforcement learning. So reinforcement learning is a technique that's used today in games like chess and Go, where AI-based agents beat world champions. It's also used in autonomous driving and those creepy like advanced robotics videos you see online. So in reinforcement learning, we have an agent that interacts with an environment. In our case, the environment is the game Wordle. At each step, the agent needs to choose an action to take. So in our case, an action is guessing a 5-letter word. And after he takes an action, he receives from the environment 2 things, a state and a reward. The state is kind of what happened as a result of you taking that action, or where are you now in your environment. And the reward is supposed to incorporate how good your action was. So we're going to focus on the reward part of the model. The reward function is a crucial part of reinforcement learning settings. It's the motivation that lets the agent learn what's the difference between good and bad actions. So a good reward function successfully balances between short-term rewards and long-term rewards. You can think of it of learning a full strategy as opposed to learning a good specific move. For example, in chess, a good reward function would reduce points for being eaten, but it would also learn a full play of sacrificing a piece for a later conquer. We can create many different reward functions. I'm going to show an example of one for Wordle. It has three components: a shrinkage factor, a correctness factor, and a winning factor. So the shrinkage factor gives you points for eliminating possible words or shrinking the possible word space. The correctness factor gives you points for guessing correct letters. And the winning bonus gives you points for winning the game, guessing the correct word. So for some intuition, here are two examples of how we calculate the reward function. Let's assume the target word is maple, and we're on the first guess of the game. So we're going to compare guessing the word crane and guessing the word fuzzy. Now, none of these two words are the target words, so for the winning bonus, we get 0 points. After guessing crane and seeing this pattern, we're left with only 49 possible words left, meaning this guess shrinked our possible word space times 47, as opposed to fuzzy, which shrinked our possible word space around times 2. And at the end, for crane, we get a reward of 50.12, and for fuzzy of 1.71. So in this turn, the agent will learn that it's better to guess crane than to guess fuzzy. Now, basically what we do is simulate a lot of games, let the agent guess a lot of guesses, and at each step, based on the reward he sees, he adjusts his mechanism for guessing a word the next time. And from these examples, you can see why you can expect him to learn like the general motion of what a good guess is. For example, you can see that guessing vowels is probably a good idea. Also why he might learn about letter positioning, because he'll get more green tiles as when the E is at the end of the word. Why even he'll learn like the general motion of what a common word is through the winning bonus, and things like that. So before we see how good this agent is, we're going to talk about our second approach. Our next approach models the problem more directly and uses principles from information theory to do so. So again, we want to model the general motion of what a good guess is. To do so, we're going to split it up to two parts. We go over all possible words at each step, and for each word, we're going to calculate how informative the word is, or how much information we expect to see as a result from guessing this word. Next, we're going to use the expected information from guessing a word to calculate how much we expect our score is going to be if we are going to guess this word. So at the end, you just pick the word with the highest expected score, which means basically what you do is guess the word that will probably get you the best result in the game. I'm going to say in advance, the next few slides are going to have some math formulas. It's okay if you don't understand them. We're going to talk about the intuition behind them anyway, so don't freak out. So, like I said, our first step is measuring the expected information. We can use entropy to do so. Entropy is a statistical measure from information theory. So what we do is we go over all possible patterns we can see as a result from guessing this word. And for each pattern, we calculate the probability of us seeing that pattern. We can calculate the probability to see the pattern based on the words that match the pattern. Now, the information from a pattern is the log of the inverse probability. And something nice to see about the information is that the more probable a pattern is of occurring, the lower the information you get from it. And why is that? If a pattern is probable of occurring, it means a lot of words match that pattern. So after you guess the word, you land the pattern, you're still left with a lot of words to guess from, and you don't advance in the game. So you would expect something that measures information to be low for a pattern like that. Now, to calculate the expected information from a word, you just go over all of the patterns and calculate the weighted sum over all of them. So we're going to use the expected information to estimate our expected score. So for calculating the expected score, we have two possibilities. Either our current guess is the correct guess, or it isn't the correct guess. Very simple. Now, if our guess is the correct guess, then our score is going to be our current guess number. So that's the first factor. And we're going to multiply it by the probability that this is the correct guess. We can calculate the probability that this is the correct guess based on if the word is in the common words list or not. It's going to be 0 for words that aren't in the common words list, and otherwise uniform over the remaining possible words. So our second option, like I said, is that it's not the correct guess. That's the 1 minus. And then our score is going to be at least the number of guesses we had up till now. And we want to add something that estimates how much guesses are we going to need from now on. So what we do is we calculate the expected remaining information after this guess by subtracting the information we have now from the expected information we expect to see, and fit it to a function that estimates exactly that. It's going to estimate how many guesses we have left. Now, we can learn this function by simulating a lot of games, and at each step, calculating how much information we have. At the end, seeing how much turns it take us to guess the word, and fit a linear regression to that diagram. Again, let's see an example for intuition. So we're going to compare guessing the word soar and guessing the word crab as the first guess of the game. Now, soar isn't on the commons word list. It's a small little eagle, something like that. So the probability of it being the correct guess is 0. As opposed to crab, where it's uniform over all common words. But the expected information from soar is pretty high, probably because it has a lot of vowels and common letters like S and R. So the expected score as a result from guessing soar is going to be around 3.16 and lower than the expected score from guessing crab. So this strategy will prefer guessing the word soar over guessing the word crab, meaning it learns to sacrifice guesses. Now, something cool about this strategy is that as you progress in the game, the probability for the words in the common words list increases. So what this strategy learns is that at the first 2 guesses of the game, you sacrifice guesses for gaining more information. And after that, because of the probability increases, it will go for the win instead of collecting more information. I know the tension is killing you. So let's see our final results. So both of our machine learning based approaches were able to beat average human performance, even though it's optimistic human performance. The reinforcement learning agent achieves an average score of 3.77, and the information theory agent achieves a score of 3.42, and that's also our best strategy for today. There's a theoretic proof that proves that you can't get lower than 3 average guesses in an automatic solver. So the information theory agent is pretty competitive, and it's also the best score I know of. That's pretty much it for today. So some takeaways from this talk. Though it's not always true, in our case of teaching an agent to play Wordle, machine learning practices can help us. We saw that both of our techniques led to results that are better than average human players. Now, between the lines, there's also a lesson here about the importance of baselining. To justify using machine learning, you need something to compare to. In our case, we compared to both simple programming and to human performance. And we saw that machine learning can bring us results that are significantly better than both. Now, we saw how we can use reinforcement learning and information theory to play Wordle. And both of these approaches can easily be generalized to other games or be used in other domains with a few adjustments. So we also saw the Wordle benchmark package that can help you try out your own agent if you want and compare it to the results we saw here today. As a bonus, I added the question everyone, I think, came to the talk for. So what's the best starter word? The answer is it kind of depends. So letter frequencies is going to tell you that later is the best starter word. Information theory says it's Saleh, reinforcement learning, the reinforcement learning agent converges to stare, which is actually the word I start with, but never mind. And the other approaches I saw online say it's raise or trace or crane. And there's a lot of different options. It kind of depends on what the strategy you use afterwards is. In my opinion, because as human, we can't exhaustively go over all 5-letter words in our head. Start with whatever works for you. I added the resources to the talk here. If all the code is available on GitHub if someone wants to see it. And thank you for coming. Questions? Yes, in the back.
So you're trying to plot a computer engagement. I'm going to go back in time. Watson did Jeopardy and won against the 3 best players in Jeopardy that were ever made before. How close is this?
Close to what? Like
beating the best human. Does it beat the best human at this time? You're saying most of the time?
So I don't think there's a definition for the best human, but the project I showed about the average human also calculates the best score in each city worldwide and things like that. And the lowest was around 3.6. So I think it does beat the best human players.
Thank you.
Cool. Anyone else? Questions? Yeah.
There's some words in Wordle that many people get on a few guesses, and then there are other words that most people, if you look at, they compare in social media, will get them on like 4, 5, and 6. Did you compare specific words to see if algorithms work differently on specific words versus others? Because Wordle does have a lot of uncommon words too.
Yeah. So just a fun fact, what a common word is just the developer's girlfriend going over words and deciding if it's a common word or not. So like you said, there are words that I don't think are common in the common words. No, I didn't take a look. You're not the first one to ask. I heard someone else asking about cognitive dependencies you have when guessing words. So maybe that's related to why there are some words people guess faster than others. I think it might also be related to just how it depends on the letter of the words. Words with informative letters you'll guess faster because that's usually what people start with, I think.
Yeah, I know, but I'm saying if you have the same word, if maybe there's specific words that humans do better than the machine learning approach versus the opposite based on, or is it always the machine, to algorithms and machine learning, some of them work better in different subset of words?
I didn't check, so I don't know. Sorry. Anyone else? Okay, so we have a break. Thank you.